Hello and welcome to our presentation on continuous monitoring and ESA in the wind. We're going to do the presentation. I'll be watching for questions during that period. If I'll answer them during the presentation, but we'll also answer them towards the end as well. If we don't get to all the questions, I will follow up with those after. In any case, let's go ahead and get started. So electrical signature analysis is not something brand new. It was developed by Oak Ridge National Labs in the 1980s. A gentleman by the name of Howard Haynes. That animation on the right is from one of his presentations. It's been applied in the nuclear power industry. That's what it was originally developed for, in particular for motor operated valves. Contrary to popular mythology, the original purpose of the technology was not to test rotor bars in electric motors. It was actually to detect wear on the gears in the components of, and bearings, of course, in the components of the motor operated valve. In fact, the patent, which was issued in 1989, specifically does not even mention rotor bars. Instead, goes on to expand it to cover fans, pumps, and other applications. It wasn't until later, in the late 1990s, that we began to look at it for more power generation. Right around 2003, actually, I was doing testing on smaller turbines in 1997, but 2003 was the first utility scale site that we did some work on. So we're going to cover a fair amount of that as we go through. Electrical signature analysis itself, by definition, is basically looks at both the motor and load for current. Voltage looks upstream towards generators. We use it in the industrial sector as well. So if I have two identical machines sitting next to each other, I can compare and determine if I'm looking at the machine next to the machine I'm testing or the machine I'm testing by looking at the waveforms in either voltage or current. It will also do power quality analysis, and several of the technologies do torsional and kilowatt analysis. The one we're talking about here does all of the above. Again, Howard Haynes, his presentation from 1989, he gave me this slide as well. Takes a look at how they relate. So motor current signature analysis was specific to just an electric motor. Current signature analysis is for electric machines and driven equipment downstream from where you're testing, and voltage signature is upstream from where you're testing. All of them combine into power signature. And of course, it goes relatively quickly. And I'll give you a little heads up. When we go on to a site, for instance, one of the sites we did here in Illinois, we had just over 100 turbines to test. That took us 2 days. So it was record. Actually, we hit a point where we were doing 9 minutes a tower, including traveling between towers. So it's a relatively quick and painless test. The total time for the technology we use is about 48 seconds. And I'll do the commercial aspect of that in a couple of minutes. But in any case, the transducer for electrical signature analysis is right in between the rotor itself and the stator. That air gap right there, the magnetic field is the transducer, not the rotor, not the stator. We take our readings off the stator, but the details are from that air gap. That, by the way, does include transformers. So on the right, that's an ECMS1. That application there is actually not in a turbine. That is at a factory connected to their utility meter. We have a revenue grade of 0.2. So in that magnetic field, a lot happens. So everything happening coming into, going out of, or coming into, and basically everything that goes on um, across that energy transducer, whether it's a generator converting wind power through a powertrain to electrical energy, or an electric machine converting everything back from the electrical energy to mechanical torque. Everything happens through that magnetic field, which makes it a system-wide transducer, meaning that when we look at electrical signature analysis, we see the entire system, all components of that system at once, versus your point transducers like vibration and other things where you have to have the transducer in line with the particular item that you're concerned about. So everything up through small torsional vibrations and torsional issues that occur as a machine is trying to drive through a defect or hesitate through the defect. That's one thing, but more so, the secret that they discovered at Oak Ridge was that small side-to-side movements of that rotor inside that air gap follow what's called an inverse square law, where small changes come out and show in larger torque. The challenge, well, with wind turbines, there's quite a bit going on. This study was done as part of a presentation we did at OEA in 2018. This was the Shermco portion. They took a study of a number of different generators that they'd received, wind turbine generators, and identified the problems. Now, bearings are automatically replaced, so of course you're going to have a large number of bearings, but they actually determined that the majority of faults were actually turbines. They saw a lot of stator wedge issues. An example there is on the left. I'm going to actually go through this case study. We were asked by Acciona and others to do a study on root cause analysis as to why they were losing wedges, and the end results were quite fascinating. The rotor, in particular, the wirings and wiring fractures. And the other mythology we'll touch upon is everybody thinks it's a particular GE design that has this issue. It is every wound rotor generator in the wind industry will end up with a fractured wiring at some point in time. Collector rings as well. That's you'll see me refer to that as the brush circuit. Stator issues other than that, and then rotor leads and so on. So anyways, the thing that we thought was a big issue at the time were magnetic wedges, and turns out that was not the case. Electrical signature analysis did not really get fully utilized in the, well, it's not fully utilized yet, but get more so utilized within the wind industry until the detection of wirings. Another study done, and this was presented at now ACP, but we at the time, across 430 generators of the 1,700 that had been tested with this focus in mind, from 2017 through 2019, 430 we had confirmed findings, meaning that we had feedback saying that yes, those conditions did exist. This is the breakdown. So generator wedges were about 4%. You notice there's a lot of mechanical things in here. Another one we found interesting was blade unbalance. So that means that the blades not turning at the not turned at the same degree as each other. It's kind of interesting because you'll find that type of thing gathers by site. So some sites are very good at some of this, some are not. So we'll see things like that. Miscellaneous gearbox faults, primarily that's gear meshing and bearing issues and so on. The wiring and brush rigging issues are down here. They come up to be about a quarter of the conditions that we find. Because we are taking a look with all of the methodologies, we are able to and have at this point now well over 3,400 tests in our library of different designs. We do project out what we expect faults to look like. And what's particularly interesting, because of the nature of this technology, the actual load doesn't matter. So if I go and take a look at a turbine that's just in cut in versus one that's seeing, say, 20 meters per second, the faults show up basically in the same way and at the same peak. So it's kind of fascinating how that works. But in any case, very few times do we say something's in excellent shape. More so it's monitoring, which is B. C and D, pretty much if there has not been any monitoring going on and we go to a site that's has at least 10 years of application, we start seeing a growing number of wear issues. So Y-rings. Well, on the left, that is a catastrophic Y-ring failure. Usually means that the generator is being replaced. The idea is to catch it before then. So that generally runs a cost somewhere somewhere to the tune of 150 to 200,000, not including all the energy losses while they're waiting for a crane, things like that. On the right, that was a fault caught just before failure. So normally we'll see a separation of insulation. This one here is, I believe this was a Suzlon. Suzlon also used to do a little bridge across these to try to get them to run longer. We run into that fairly often. I'll get into some of the false positives as we go through it. But in any case, that's normally what something may look like. Of course, gearbox issues, we found a few extremes. This is smeared planetary gear. This would be the outer ring. This is a planetary gear itself that fractured. We do see those pretty readily, well before it gets to that stage. I'll often, if I'm not doing continuous monitoring, if we're doing data capture, most people that go with us will normally see, or with the when we teach the service companies that do this as a service as well, we train them to identify that you'd usually want to take more than one reading. Because if you have wind gusts in certain applications, if I see a wind gust and the wind dies, I'll see some chatter in a gearbox. If I see that chatter also exists as the wind's increasing, or the power is increasing on the generator, then I know I have a condition where I need to do something. So there's some tricks that you need to do sometimes with the technology, but pretty much, even if I get a single shot, we have some wind sites that do their own data collection and ask us to do the analysis. We'll get that data back, take a look at it, and be able to tell them even off of a single data set. And then of course, main bearings. One of the most common issues we see in the main bearing is when these are in place, when they switch out the grease, we'll see grease collection down in the bottom will start to dry out, and the rollers have to then roll over that. That shows up as an outer race signature on the main bearing. Now these are running between 14 and 20 RPM, making them quite challenging. And on the right, no, we don't quite catch them. We'd like to think we'd catch them a little ahead of that, but if we have certain types of defects in blades that cause an impulse, it's every time the blade passes the tower, there's an impulse that's seen through the entire train at the RPM of the blades. So that will show up in the signature. If we see a peak, because they'll normally be averaged out by the software, if they show up as a peak, then we know that there's a condition that needs to be evaluated. So just to get into the technology real quick, it is basically the great grandson of the testing technology used at Oak Ridge. It's built by Framatome, which is a nuclear service company. MotorDoc, developed the methodology for testing wind turbines, as well as a number of other things, and are in partnership with Framatome on non-nuclear work. So it's not something brand new. It's been around since the early 1990s. It's gone through a couple of iterations. The latest one is nice and portable. So that upper left one there, that's National Institutes of Health. We're testing a 13,800 volt machine. So voltage doesn't matter as long as we can get to CTs and PTs. You do not want to connect up to, with any instrument, you don't want to connect up to anything over 1,000 volts. So this is fully capable of handling any turbine. As a matter of fact, the one that we'll cover with missing wedges, those are 12 kV machines. Lower right here, this is actually an S97, so a Suzlon DFIG versus their SFIGs. We did a number of sites. There are not a lot of those out there, but they're a nice low wind machine. We found it's far easier to collect on the low voltage side. So I'd say about a majority of our work is collecting data on the towers and then analyzing it. And of course, being the lazy engineer that I am, it's almost all automated now. So we'll cover that a little bit as well. So our internal machine learning bit, we've actually converted it back to an expert system. I'm working on a more advanced system now, along with the programmers. So this here is the original continuous monitoring device for empath. It'll take 32 machines in, not cost effective for a wind site, unless you're doing all of the machines in a tower, then you would go with a variation, but there's 32 machines done with that. All of these are Windows based. By the way, as an edge system, what's kind of cool is that the people who have the device, you own the data. So it can be kept locally, it can be kept remotely, it can be kept both. You can do the analysis on site, it can be subcontracted, or even we could do it. So there's a lot of flexibility in the system. This is an ECMS 1. There's more CTs available than these, but if I'm on the low voltage side, I can put these around the leads coming from a CT and I still have accurate data. This guy here on the far left, that is an E-plug. So that is used originally with the ECMS 32. We couple it up with the ECMS 1, which is the continuous monitoring system specifically designed for wind. And when we get into it, all the software is the same. It does alerts and everything else, and all the data can be kept on your own system and within your own network. It is all, of course, Ethernet. So we have some wireless systems out there, primarily Ethernet. Just to give it some size here, they're all very small. And this one got released last week. So that's the ECMS E1. Really don't need a separate E-plug with it. So we built the E-plug inside the box. So that's now what would be used. Exact same device and same everything else that we're going to go through. So when we get the data, this is what it looks like. So including whether I'm doing continuous monitoring or data collection, software is the same. For trending, it will look at some fairly constant things. Any type of alert, it will show up from a trend. It'll send out an email or a text. This is the part that most people don't realize. What's really kind of nice is we don't have a large tech support staff. And the reason isn't because we don't have a large tech support staff. The reason is because we don't need a large tech support staff. All of the rules are built into the software, and the software is right more than 85% of the time. So this was for standard induction machine. It will do everything, including identifying bearings. And if I were to go into the bearing section, it would tell me which component of which bearing. These are what we have algorithms built for on the left, for identifying faults in different types of systems. It very easily handles via variable frequency drives. Matter of fact, you see the VFD there. I usually just leave it set on induction. It's still going to find my speed for me. It's still going to find everything else. Transformer, I use these a lot right now in several energy studies we're doing. Down here where it says asynchronous generator, that's now set up for wind turbines. So that is very specifically meant for wind turbines. We'll get into that in a minute. Scheduling can be as, well, now we got it set up for up to every 5 minutes, but you could set it for once a week if you wanted to. This is just what's sent out in the email with the alarm. And this is what was set up for wind turbines. So when I put in gearbox information as well, it will identify if I have a potential wiring. It wants to trigger you to go take a look, because wiring can also look like, or a bad brush or even a shorted shunt on a brush could look like a wiring. So there's specific things we look for in that. Then this flags us over to here. Programmer is colorblind, so he thought this was red. So that green is red. But in any case, these I can highlight and it'll take me and show me where those signatures are in my spectra. But it will flag everything that it sees. And down here you see the power loss. So for determining how much damage is going on in a gearbox, we look to this. That actually gives us an idea of the severity of an issue. How accurate is it? Well, we've been out at sites where they've been able to compare within a kilowatt of what we're finding in their own data. So let's get into this a little bit. And just to put the teaser out there, in the end, I am going to pull up a signature from a wind turbine. As a matter of fact, one that was tested recently. And we'll go through the analysis of and how it's done. Where do we collect data? Well, we used to collect data right off the power side. So the CTs would go right around the high voltage end, say on the right, that's a 1.6. We used to go in through the back. On the 1.5s, we used to connect just above K1 for voltage. Nope, as a matter of fact, the one on the left here, that is off of a 1.5. We've identified where to get good data off of the low power cabinet. So in many sites, we don't even have to turn the towers off anymore if we're doing data collection. Those are the same points that we would gather data for the continuous monitoring device. The one in the middle, that's an S88. We take it right off the green box. Top is current, bottom is voltage. All we have to do is match up. So if I 1, 2, 3, I put on 1, 2, 3, because part of what the software does when it's analyzing is convert everything over to kilowatts and air gap torque. So once it's hooked up, you push a button, and 48 seconds later, it tells you exactly what it sees. There are times when we're on a site and we've said, shut this down, you've got a bad wiring and it's serious. And they'll say, well, we'll get to it in a week, and it's gone the next day. So it's pretty accurate. Other times we're seeing 11 to 14 months out. So if we say early fault, it usually means you've got some months to make plans around it. What the data looks like, and what's really important is the resolution, because a lot of the peaks, because I have multiple speeds ranging from 14 to 20 RPM, all of the speeds of all of the components in the gearbox, all of the bearings involved, and then the generator, whether it's running at 20 hertz or 30 hertz or 1200 or 1800 RPM, or if it's overseas, maybe 1000 or 1500, it comes in. Now, I say that because that's very important to understand, is the speed. And I mentioned magnetic fields earlier. There's a difference between mechanical speed and magnetic speed. So that's the crucial difference that most people do not pay attention to, even in vibration. And I'll cover that in a little bit. So anyways, once the data comes in, my higher resolution, low frequency data, I get current, I get voltage, then I get a current FFT, a voltage FFT, and then DMOD. DMOD is kind of there so I can identify my speeds and possible peaks. Do not ever use this to troubleshoot. It'll steer you wrong. You need to be able to reference to something. And I tell vibration analysts, the difference between electrical signature analysis is standing on your head and crossing your eyes or drinking heavily. You've got peak pairs of everything, and you're measuring from the top down versus the bottom up for vibration. So I will have, say, my peak in line frequency, say here, this is a motor, this is not a, so if it's at, if that peak is here, I'd be counting down to that next peak in decibels. So this is electrical pressure, more or less. So it's a measurement of force. So it's dB down, so it's relatively the same. So if I start changing loads, it'll be relatively the same. Now, because I take 12,000 samples per second, that gives me a Nyquist of 6 kilohertz. 6 kilohertz covers everything in a turbine, including harmonics. So normally in a turbine, the firing frequency on the rotor drive, if it's a defig, is going to be somewhere around 2 kilohertz. So somewhere around 2,000 here. So I'll see that, and then I'll see something around 4,000. That I can use to determine if I have an issue, and I'll also look at, there's a set of peaks in between that will identify issues with the transformer. Down here, we'll take a look at this later. I normally don't look at this in dB because in power, it'll actually show up as kilowatts. And when I convert it back over to linear kilowatts, the peaks are exactly what I'd calculate in vibration and relate to the losses that I'm looking at for that particular defect. I use that in the commercial side to identify, in the industrial side, if we see, say, bearing defects or misalignment or some other condition, we can identify the energy loss due to that frequency and the related greenhouse gas emissions. So, and then here is my instantaneous air gap torque. So this is the time waveform, and on the right, this is the FFT. Need a sip of coffee here, pardon me. And then, of course, we can do all of this in a waterfall plot, which becomes very important in a wind turbine, as things may vary in speed by a little bit. If I see a wide base, that's either going to be looseness if it's continuous, or it's just a variation in speed. So we need to take a look at that. In our machine learning programs, we actually have that built in on how to analyze it. First case study, this is from, well, the story went like this. Guy by the name of Chris Petrola, he did this presentation, so and he has a paper on it, so I'll blatantly use his name, called me up from Acciona and said, can you detect fractured Y rings in wind turbines? Having just looked at wound rotor motor problems on an overhead crane in a steel mill, I said, of course, it can't be that difficult. I have a theory. So we went ahead and tested 40 machines up south of Calgary. And they had already done a survey. They had identified 20 machines that had visibly fractured Y rings with borescope testing. We went up there and set aside 5 days, a day and a half into being there with half of one of the days having no wind. We had completed both sites. So, and then we came back and we had identified 21 that had issues. So they brought in Delhomme, and Delhomme came in and from Quebec, came in and replaced the Y rings and recorded what their findings were. And this is what they commonly found was a fracture. Normally with one fracture, you're in bad shape. Second fracture, you normally have a catastrophic fault. This is the worst of them. They found 2 physical cracks in this one. And this one was the 21st that we had identified was a partial fracture. Well, how can that be? So they said, well, what was your theory? And I said, very simple. If I have a resistive or impedance unbalance in the circuit, it causes a change in the magnetic fields in the rotor, causing a bulge. So I end up with 2 conditions. One looks like a broken rotor bar, which is pole pass frequency, and the other one is dynamic eccentricity, meaning that I'm magnetically orbiting. The rotor may be dead center in the generator, but it's magnetically orbiting inside the stator. So normally it's performed between the transformer and the generator. So we're not, basically the idea is to get where I'm producing the most power. In a DC machine, I take off the armature. In a motor, I take off the stator. And in a generator, I take off the stator. Challenges we run into. Well, there's a lot of variability in wind, so we have to account for that. There's a number of issues within the turbine and driven equipment. We recognized many years ago that there was some subsynchronous resonance going on. It wasn't until later when we were doing a research project for a site in West Texas that we identified that some of those conditions may be coming back from the grid versus just the resonance occurring between the transformer and the generator circuit itself. There are many defects that are within half a thousandths or half 0.005 hertz of each other, and we have to be able to identify those. That means very, very tight resolution, and some of it looks like noise. So let's take a quick look at wind. So this goes back to the wiring failure. This was 2010. We did an RCFA. It was pretty advanced, looking at the reason for missing wedges. This was a cold weather machine, northern Minnesota. And basically, one of the discoveries we had was the plastics being used were not able to manage the minus 40 degrees centigrade that they saw on occasion. All this brown, by the way, is magnetic dust from the wedges. And of course, when that occurs, that stuff eats away at everything, but it does something else pretty cool, and that is something that Nikola Tesla used to demonstrate in the past called magnetic termites. So all that little ferrous material gets on the winding, starts spinning and working its way into the insulation system until I get a track and it blows to ground. So we found that across a number of different generators. Now the repair shop I was running at the time, we did not use burnout ovens. We used a warming methodology. So we pulled the coils out. And then we discovered we didn't need to actually warm them up at all, that they just came out, which had us look closely at the tolerances of these coils going in, and discovered that they were loose in manufacture. Some as much as 40 thousandths. So you're supposed to have less than 10 thousandths on a side, and they were relying on glue, the VPI, to hold them in place. And they would start to eventually move due to thermal cycling and then beat the wedges out. And then those would disintegrate in between the stator and the rotor and worm their way into the winding and cause the failure. Now, what's really kind of cool is that's the number of stator slots times the RPM plus and minus the line frequency. That's the signature. If we see that signature, then we know we have that kind of issue. We can tell how severe it is because we know that a short's going to start to occur between conductors. This is after we took the layers off. This is the actual conductors and where one failed. We'll see a winding stress signature. I published that in IEEE year before last. and it's basically a turn-to-turn short, or shows like a turn-to-turn short. These are just pictures of the termites working through that insulation with a 10 power microscope and some of the arcing that occurred. In any case, that would happen. Well, it's detectable. So before the winding fails, we're seeing insulation related issues. That, by the way, is the generator that had the catastrophic failure of the winding that I showed early on. Big problem in towers, of course, is they turn off, turn on. A lot of people turn their space heaters off, probably trying to conserve a little energy. Problem is the machines cool down all that faster, and there you go, there's your thermal cycling, and then the coils start to come loose. Okay, so let's get to that SSR issue and what signatures look like, and then that will give us time, because I'm a little ahead of time. Oh, and then we're going to also cover the detection of a bearing before and after in a generator. So this was a study we did after the big freeze in Texas. This particular site was seeing a large number of failures. Matter of fact, while we were doing the study, before we even approached the tower, that they had suspect, it would fail. So they were failing at a very rapid rate. This is the other thing we get to do, and that is a startup analysis. So from right when the 1 second before the generator starts to, in this case, 240 seconds. So this was interesting, number 2 right here. And then the soft start kicks in. Now these are 1.5s. So these are GE 1.5s. And then I'll show you what this part here looks like. But this part here we found fascinating. Is being an industrial type, we normally start our machines up and bring them up to speed. Very rarely do we start spinning something up to speed and then activate it, causing the entire system to shock. And then for systems of this size, very rarely will you ever see us try to start something anywhere from 6 to 12 times in an hour. But that's what we see in wind. So a machine might be loaded and unload, cut in and cut out many times an hour. Insulation systems and mechanical issues don't last very long in those conditions. Now, that very long doesn't mean days. That could be years. So right now we're seeing an average before we go to a site. If a site has a lot of wind conditions, I'll show that in a second, but a lot of variable wind conditions, based on our history now, we put in an extremely accurate estimation of how many towers we're going to find with different types of problems. So this 2 right there, that is an impulse from when the breaker closes. So I have voltage down below, and then the breaker closes, and that causes that shock in the system even before the soft start. And it doesn't matter whose design it is. For that site, some of the towers, for whatever reason, somebody decided that we wanted to test up tower. Which part of the benefit of this technology is if the controls are down tower, I don't need to climb. And if you ever meet me, you'll understand I'm not into cardio. So we clipped on now, because I'm only clipping on around one conductor of each phase, that's just a CT ratio of 3 to 1. When I get this, I will normally not pay too much attention to loose connection readings, because we will detect loose connections. They often happen in the connection box, but and then voltage clips here. So we'll put a CT ratio in. For the particular study I'm going to show you, we were right around 5.3, so right around here on the power curve. This is part of what we look at for our 5.8, sorry. I've got it right there. So we were somewhere around 300 kilowatts roughly on the power curve for that tower. We did have gusts. It was 13 degrees C, meaning a little chilly. And then this is the history across from the time that they started the site till present, we take a look at that with a little machine learning tool that we have and apply some other things, and that gives us the chance that a tower has an issue. So we will not be publishing that. We do not want insurance companies to get their hands on that one. In any case, then we took, for the most of them, we actually took the data in the base of the tower, so we didn't have to shut it down, and we didn't have to have people climb twice on a tower. Very rarely do we do that. And for your GEs and Suzlons and several others, you don't need to. It's all taken down tower. Siemens and a few others, you do have to go up. So let's take a closer look. Here is the transformer readings. When I see readings this high, that usually means there's going to be a resonance. You'll notice that it's in both voltage and current. And you notice I'm looking at both. Why would I look at both? Generators are voltage, right? Well, the reason I look at both is because of this power curve. And as I introduce all my VAR correction, I have multiple different machines. Sometimes the rotor's a load, sometimes it's a generator, sometimes other things occur. So I literally have to look and troubleshoot off of both voltage and current in a wind turbine. So we look at both. Number 5 in between on the top left and number 3 on the bottom right, those are signatures showing that we're going to see a ferroresonance in the transformer. What that translates to in English is that means we're going to have heating. We're going to see high levels of gases, dissolved gases in the transformer. So that's right at startup. That's during this period. So in the software, when I lock into a period like this in the window, physical window here, is what we're analyzing on the right. And then down here on the lower right, that's the steady state, and you can see those signatures still exist there. Now, if I don't have it hesitate on me again, so it looks like our viewing goes in and out a little bit. Sorry about that. They're still working on our infrastructure here. Oh, I'm sorry. This is, by the way, this is what a rotor looks like. So there's the firing frequency and multiples of it and so on. We normally don't collect data there. That was actually by accident. Clipped around the wrong cable going up the back of the tower. If this comes through okay, what you'll see, this is a video of that tower that I just showed you, and just showing that the harmonic and the transformer signature, the firing signature of the drive, and the first harmonic of it, or second harmonic, I'm sorry, and the resonance signatures remain steady. And the other thing we saw was in that air gap. So unusual for us to see harmonic distortion in most towers. We saw some in these. Most likely that's just the setting. But on the right-hand side, this is across that 140 seconds. Actually, it's 80 some seconds of that. But on the left there, you see those two double peaks. That's the air gap torque pulsation from that first closing of the breaker. And then you can see the amplitude increasing as it's coming up to speed. Because of the location of that site away from heavier loads, quite a ways actually, and the fact that they hit a 500 kV line with linear capacitance, they actually had a very high SSR or subsynchronous resonance. It's referred to as torsional SSR, torsional interaction and control interaction in a wind turbine. Most studies, there's a ton of them published. Anybody ever goes to IEEE sites, you can look them up. I've got a pile sitting next to me about 18 inches high of 4-page studies and 2 books on the subject. Found it very interesting, and even more so when we got our hands on some wirings that hadn't quite failed yet, and the generators were removed for other repairs. So that one of the repair shops, Shermco in particular, had sent me this. they've been participating in the studies, as has Evans, as has H&N. But it turns out that all those Y-ring failures are fatigue related. So flexing. So as I have starts and stops, nothing, it's not stationary, it's moving. Part of the reason why the Hitachis seem to go first, they have a slightly thinner Y-ring than some of the other ones. And some of the ones that have the thicker Y-rings last longer. But I guarantee you, for a fact, every manufacturer has that problem. Several of them are now using our technology to do studies on that very thing. So this circuit right here introduces some of that. However, big thing to remember is it is correctable. So part of what we're working on with some of the companies, and we're trying to get it through ACP as well, is working on methodologies to reduce that wear and tear on the towers. There's no reason you should have to replace a Y-ring or do repairs in a generator twice in 25 years and replace a gearbox once in 25 years. So let's cover that bearing real quick. So this was, yep, we do testing till the cows come home, haha. So in any case, these are 1.6s. There's one of these towers here where a service company went out and replaced some bearings on a generator. They did an after test, saw a signature, and so they were going to do a before and after test, happened to have the identical conditions in both cases. So same wind speed, same everything else, made for a perfect case study. So data. There were a few other issues going on in the tower, but you can't cover them all. So this is before. They did have some planetary gear alignment issues and a few other things because everybody forgets to align these things, including on the main shaft side. Just because you bolt it up and there's a rabbit fit does not mean it's aligned. And on the generator side, there's some folks thinking that you don't have to align a generator to a gearbox. Those of us in the repair industry want to thank those folks because it gives us plenty of work. So in any case, there are a few issues with the tower. Part of the study was identifying some bearing stuff, so inner and outer race, small defects, and we even saw some ball spin frequencies. Those all showed up automatically. So to bring it in close, by the way, for those who have vibration experience, the multipliers are exactly the same. And you notice this speed here. They called back and they kept telling, well, you're wrong because it was actually turning at 1300 and so, and nope, it's turning at basically what amounts to, I think this was 1218 CPM constantly. Well, it can't. It's doing, nope, it's turning at 1218 RPM constantly. But no, the TAC says it's, nope, it's turning at that. And the reason it's turning at that is because the magnetic field is turning at that speed. Otherwise, I'd have something other than 60 Hertz. And I can actually use my line frequency to give me an idea of where I am with that frequency. This happens because in a wind turbine, I have the turning frequency, and then as part of my correction, using the drive or using up tower control in a wound rotor machine, is I create a counter rotating field in the rotor as well, so that the field between the stator and the rotor is turning at something close to the number of poles of the machine times the frequency I'm interested in. So in a 60 Hertz environment, a 6-pole machine wants to operate 1200. Now, if I go under that subsynchronous, so that my speed is less than 1200, then I won't generate power. So I have to go above 1200. So I'll do a pro-rotating field, and in some to whatever the set point is. And then in the other case, I would do a counter-rotating field to slow down the magnetic field so that the fields cutting the stator and producing power are actually showing up as close to 60 Hertz as possible. There's the secret. So when I start taking a look at it, and what's even cooler is everything on the powertrain side of that air gap, including the generator, all the multipliers translate backwards. So they translate to that RPM. So I'm not hunting for RPMs other than, it just translates backwards. We actually figured that out when testing active front end drives, being able to test through those variable frequency drives because they don't have a DC bus, the translation backwards. We're publishing a paper on that next year. So in any case, down here, these are the signatures we saw, plus there's an extra one. So this one here is the thrust bearing in the high-speed gearbox. And we were trying to figure out why we're seeing the signatures. Well, as it turns out, there was an incorrect spacer in the coupling, putting a little extra force on the thrust bearing in the gearbox. So that showed up, and it caused some wear and tear and other issues on the bearing. So I pulled the bearing out and shipped it to me, and then put the new bearing in, and I'll show you what those results look like. So here's the bearing. This is what an M bearing is, an insulated coating on the outside. You know, probably the best one. Some people tried putting coatings on the inside. Don't even get me started on that. Shafts expand and contract, and ceramic doesn't. In any case, we were seeing on the inner and outer race false Brinelling, basically. These don't look like much in the pictures, but they're pretty rough by hand. So those were actually visible with vibration as well. One of the balls was skidding, so it was already starting to flake, and this is what they should look like here. So some of these were getting caught in the cage. I don't have the cage, or did not have the cage to look at that as well. So those are the signatures we saw. We had 2 like this, the rest were okay. And these are pretty sizable. The one that was put in, notice down here in the lower left, this here on the right is the kilowatt rating. This is the scale. Here, you notice that all those peaks went down very low. These peaks will always exist. By definition, you have friction and other conditions inside a bearing. So you'll have some level of peaks. They'll be lost in the noise. It's when they come up. So on the left-hand side, you see we dropped down from 11 kilowatts loss across that bearing, or those bearings, to about 2.4. And that's because I'm only calculating those peaks. And of course, some of those other conditions still existed. So I'm going to do a quick walkthrough. I don't see any questions at this point, but I'm going to do a quick walkthrough of what an analysis looks like. Oh, let's get out of there if we can. There we go. So here we go. As you can see, done a few. Let's get to, yep. So this is, I took these are all real sites, real generators. And I've just unnamed them. So we'll look at an S88 first, because S88s have got their own idiosyncrasies. Not sure exactly which one I picked up, but this one actually has the running speed being correct. So they caught this at just the right time. So this is a 4-pole machine, in this case running at 1831 RPM. Pole pass frequency looks wrong. No, there it is. Sometimes if I don't see something, I'm going to try to look right around 1 hertz, but that's not the case here. So before I show you the signature, let's see what it thinks it sees here. Loose connection on 1 phase, misalignment or unbalance, and then that would be a bearing in the gearbox. Now all those multiply, and then of course down here is only about 1.2 kilowatts lost in the gearbox. Now just so you can see, there's the nameplate for the generator. Under equipment, these are all the multipliers. You can see there's blank spots there. They just didn't have the data for that. We have a library of gearboxes and an agreement with one of the gearbox repair companies to get us data when we don't have it. But in any case, that's that. So let's take a look. So on the high frequency spectra, running a couple of screens here. Let's get rid of some of that stuff. Sometimes I'll do this just to get a look and see what current looks like. And see this little wavy spot here? If I look at voltage and I see that as well, then I might have a little more concern that I might have something else going on. Nope, nice and smooth. So this could be something with the gearbox causing hesitation. This could be an actual load. It could just as likely be something going on with a wiring or brush circuit. But let's take a look at our data. Well, first off, my misalignment or unbalance, that is right here in both current and voltage. So that's my one-time RPM. One-time RPM always says misalignment or unbalance. It's not like with vibration where if I have 1, 2, 3, 4 times the running speed that would show up. No, that's the other. Now, in here, because my frequency is a little higher, I have some tiny peaks associated with the pole pass frequency or the pole pass sidebands, not so much in voltage, so it didn't call it. These inside, people make mistakes and think that is a rotor issue. Those two peaks right in there all the time. But if you don't have this type of resolution, that would all blend right in and show up. Those are the blade pass frequency. So that's how fast the blade is passing. So they have a little bit of an alignment issue. This is our 4th test on these towers. This particular company does their own data collection. So we'll see that, and our report back says, hey, you might want to check the alignment of those blades. Now with a Suzlon, these peaks always show up. Those relate to the gearbox. Nothing, I always see them. Really not much. We've attempted all kinds of stuff with one of the companies, wanted to see if they could improve on their gearbox. So we know that if we see these, they're there. We do know that there's other peaks that tell us when something is going wrong. So unlike when I show you what a GE looks like, this is very unique to Suzlon's. So we just accept that as a signature. Now the one-time RPM, these other peaks are, by the way, other things going on, such as this. Okay, so there's my peaks there. So I don't have to sit down and calculate them, but it's basically all of those components times the RPM plus and minus the line frequency, or plus from the line frequency and minus from the line frequency. It's a mirror, or should be. And there's another little dirty secret in the industry. Some people with limited experience, to put it mildly, that manufacture some equipment said, hey, if the peak's higher on one side versus the other side, then it's this signature. If it isn't, then it isn't, and they're wrong. The reason has to do with which type of windowing they do. I always use flat top. There's a little more noise, but I usually have balanced results. So in any case, and for those that are into vibration, then yeah, it's all the same. Let's take a look at that high frequency data set. And for fun, let's take a look at the waveform. There we go. And there's that waviness again. And notice the phases don't look, this should all be about the same, but they're a little off. Another thing is this is sinking under. That happens once in a while. So let's change that here. They never go under minus 120. That just tells me they're in relatively low wind speeds. I can also tell they are because of all the noise here. There's a lot of noise there. So that would be low wind speeds. Those are probably some of the gusting. So once I notice that, then I'll do so much. And I see some ripples sitting across. Now this is across about 10 seconds. Let's get rid of those. And just to make life simpler, let's get rid of those signatures. So we're just looking at one phase. Much easier to see. There's the second harmonic of the firing frequency. So if I bounce back, the other one's going to be somewhere around here. and very low resonance. So I know where this is. So they actually have some relatively heavy loads nearby. So they're not going long distance. Power harmonics are very important because I don't want to show those, but I don't want to make a call based on those. So if something lines up with my with the line frequency peaks here, I'll ignore that. It's just a harmonic. So if I sink down here, you can see I have a little bit of static eccentricity. Some peaks align with it, both in voltage and current. That means that I have some soft foot as well. So I have some misalignment with soft foot. That's my confirmation. So that's a Suzlon. And for those who are still here, let's go ahead and grab GE 1.6, the Nanjing gearbox. This is the difference. So what we're looking at here is a GE. And the other thing we're going to do here is correct my running speed. Whoop, wrong one. Yeah, that's what I thought. Okay, so let's go ahead and correct it. Okay, pole pass frequency is obviously not there, and this is a 1.6, so my pole pass frequency will be here. There we go. Notice that right there. That is my wiring signature. So as I take a look at this one, and I take a look at some of the conditions, I have main shaft bearings. The generator bearings are okay. Carrier bearing, problem with the carrier bearing, by the way, is not sure which, oh, sorry, planet. If you see a planetary bearing, it doesn't tell you which one, basically. So we have this. There's my signatures there. So let's take a look and see what we see. So I have some very definite pole pass frequency peaks. Right off the bat, I'm going to call this as a Y-ring. I don't have one-time RPM peaks of any significance. Pardon the delay, it's partially what we're viewing. I've got too many things open at the same time, so the computer slows down. Okay, and then the next thing I do to confirm whether or not it's a Y-ring, now those are my other signatures, is look at dynamic eccentricity. So I have some very small peaks. So that would be, and with the larger pole pass frequency peaks going on, then I would take a look at a couple other components in the data set and would call this as a Y-ring. This was, let's see, T76. So yes, this one was definitely. I don't have the after reading yet, but this was done last November. In any case, that was confirmed. So just want to check and see if there's any questions. And if not, I'd like to thank everybody for attending and appreciate your time. Feel free to email if you have any further questions. Thank you.